Redox processes 3. Electrochemical cells, Voltaic cells. Essential ideas. Voltaic cells convert chemical energy to electrical energy, and electrolytic cells convert electrical energy to chemical energy. Energy conversions between electrical and chemical energy lie at the core of electrochemical cells. Nature of science. We'll be looking at the ethical implications of research. The desire to produce energy can be driven by social needs or profit. Employing quantitative reasoning. Electrode potentials and the standard hydrogen electrode. And collaboration and ethical implications. Scientists have collaborated to work on electrochemical cell technologies and have to consider the environmental and ethical implications of using fuel cells and microbial fuel cells. Okay, single displacement reactions, which we've been looking at in the last 2 presentations. Let's look at the reaction between metallic zinc immersed in aqueous copper 2 ions. We have zinc being oxidized and the copper being reduced, and energy is given out. You can see here at the bottom, the electrons are directly transferred from zinc atoms to copper ions at the point of contact. So the zinc atom is making contact with the copper ion and electrons are being transferred. So these single displacement reactions, as we can see here, are exothermic. But is there another way to move the electrons from the zinc metal to the copper ion? And yes, indeed there is. You can move the electrons from one substance to the other via conducting materials in an external circuit. And why would you do this? The flow of electrons through a conductor will generate electricity. And this is the essence of a voltaic cell. Okay, let's look at their basic operation. You can see here that we've got a zinc electrode and we've got a copper electrode. We've got copper 2 sulfate in solution, zinc sulfate in solution, and we've got a salt bridge between the two, and we've got some wire connecting the 2 electrodes, which then electrons can pass through this wire. Here is the reaction with the zinc providing the electrons, and the zinc then goes into solution, it becomes the ion, and the electrons is given up, pass through the wire to the copper, and the electrons are donated to this copper ions to form a copper solid. Okay, let's look at the components of a voltaic cell. First of all, we've got the 2 half cells. Each half cell has 2 components. It has the oxidation half cell and the reduction half cell. Each half cell has an electrode, which is ordinarily metal, and an electrolyte, a solution with the metallic ion. To be clear, the electrode doesn't always have to be metal. So examples would be zinc and zinc sulfate, copper, copper sulfate, and nickel, nickel nitrate. The electrode terms: a cathode is the electrode in the reduction half cell, and it is the positive electrode. The anode is the electrode in the oxidation half cell, at a negative electrode. To remember this, just remember a red cat standing next to an ox. Red cat, reduction, cathode. An ox, anode, oxidation. Okay, secondly, in the components of voltaic cells, we've got the conducting material between the electrodes. This allows electrons to move from one half cell to the other through an external circuit, and it transfers electrons from the reducing agent to the oxidizing agent. It allows electrons to flow through a conductor, and therefore electrical current is generated. And thirdly, in the components of a voltaic cell, we've got a salt bridge between the electrolytes. Let's draw that in. It allows ions to move from one half cell to the other. This prevents the buildup of charge in a half cell, which would stop a reaction from proceeding. The salt bridge contains a solution of a soluble ionic compound, such as saturated potassium nitrate or potassium chloride. So, putting the whole thing together in this example, let's remember that reduction occurs at the cathode and oxidation at the anode. So we can see here that the zinc on this side is being oxidized and therefore giving off electrons. And so the zinc is the anode. Metal in the oxidation half of the reaction. So zinc is the metal in the oxidation half of the reaction. Obviously the anode is negative. And the electrolyte over here would be zinc nitrate. We can see the copper being reduced to the metal. The copper ion being reduced to the metal. So copper is the cathode. It is the metal in the reduction half of the reaction. Obviously the cathode is positive, and the electrolyte would be copper nitrate. The electrons flow from the anode to the cathode, and that makes sense. You think the zinc is giving up electrons, and over here the copper ion is reacting with the electrons to form the copper solid. So the role of the salt bridge here, the zinc ions will build up in solution here, and so you get an increase in positive charge. Anions from the salt bridge move to the anode to balance the charge, and so we'd get nitrate ions in this case moving into solution to balance the buildup of the positive charge. On the other side, the copper ion concentration decreases as it forms the copper solid. So cations from the salt bridge move to the cathode to balance this charge. And in this case, say if we had potassium nitrate in the salt bridge, the potassium would move into solution to balance that charge. Okay, you can see here in the middle, this is the cell diagram notations, how you draw the cell diagram. It's like a convention. So let's see what's going on, shall we? Oxidation half cell goes on the left hand side, and by that I mean it's on the left hand side of this double line here. The reduction half cell goes on the right hand side. The salt bridge is obviously drawn in the middle, and it's drawn with these nice two lines there separating. You put one line here is the phase boundary for the oxidation half cell, and the anode goes on the very left hand side of the whole thing. Obviously the cathode goes on the very right hand side of the whole thing, and you can see we've got another phase boundary there. And electrons would flow from this one over here through an external circuit. Okay, let's fill in this table, which shows a Voltaic cell summary table. First of all, the oxidation half cell has the more reactive metal. Reduction half cell has the less reactive metal. As we know, the oxidation half cell is the anode, which makes the reduction half cell the cathode. And the charge on electrode in the anode is negative. Charge in the cathode is positive. The half equation sees the solid metal forming the ion and releasing electrons. In the reduction half cell, the ion reacts with those electrons to form a solid. So if this electrode is forming the aqueous solution, it's decreasing in mass as it reacts and goes into solution. Whereas this electrode, solid, is building up, so it's going to be an increase in mass. Anions move to the anode from the salt bridge to balance the charge, and cations move to the cathode to balance the charge. And as we know, the electron flow is from the anode to the cathode, from oxidation to reduction. Some voltaic cells have half reactions which occur in aqueous solution. The half cell for these half reactions uses an inert electrode, which would be graphite or platinum. Here we have zinc reacting with protons to give hydrogen gas and zinc ions. So this zinc electrode will go into solution to make zinc ion, which releases electrons, which goes through the circuit to over here, let's say it's platinum. And at the platinum electrode, the protons in here react with the electrons to form hydrogen gas, which is released from the solution. Cell notation down here, we've got the zinc anode, the phase boundary to the zinc solution. We've got the salt bridge, then we've got a phase boundary between the protons and the hydrogen gas, and we've got the platinum cathode over here. Some voltaic cells have half reactions which occur in aqueous solution, as we know, and the half cell for these reactions use an inert electrode. Here's another example of this. We've got quite a hell of an equation here. We've got iron 2 plus here reacting with the dichromate ion with excess protons, giving us iron 3 and chromium 3 and liquid water. So both sides have inert electrodes here, and you can see the cell notation down the bottom. We've got the platinum anode left hand side, we've got the phase boundary for that iron 2 plus and iron 3 plus, and over here we've got the dichromate and the chromium 3 with the platinum cathode. Okay, with voltaic cells we can predict reactions given the reactivity series. So let's have a look. The more reactive metal is oxidized to its ion. Ions of the less reactive metal are reduced to the solid. Example 1. We're going to predict the equation for the spontaneous reaction of an iron aluminium voltaic cell. Well, the more reactive metal in this reaction is aluminium, so that's going to be oxidized to its ion, and it's going to give up those electrons. And the less reactive metal, iron 2 plus, is going to react with those electrons to form an iron solid. That'll actually happen at the cathode reduction. The overall equation, balancing it out. So the oxidizing agent in this case is going to be the iron 2 plus, and the reducing agent will be the aluminium solid. Cell notation. We've got the aluminium anode with the aluminium solution. Then we've got the salt bridge, and we've got the iron cathode on the right hand side. So which electrode will increase in mass? Obviously, if we look up here, you can see that the iron ions are coming out of solution to form more iron solid, and so the iron is the electrode that will increase in mass. Okay. Example 2. Predict the equation for the spontaneous reaction in an aluminium hydrogen voltaic cell. And you can see we've stuck hydrogen here. And you can see that the more reactive metal is going to be, or the more reactive element in this case, I suppose, is going to be aluminium, which will form its ion, give up some electrons. That'll be at the anode. Oxidation is taking place. The hydrogen ions will react with those electrons to form hydrogen gas at the cathode, where reduction is taking place. The overall reaction, if you balance it out, is as follows. Cell diagram notation. We have the anode on the left hand side as normal, with the aluminium solution. We've got the salt bridge, then we've got this phase boundary of the hydrogen ions and the hydrogen gas, and we've got the cathode over there. Okay, true or false questions. See if you can answer these 3 questions. Press pause and have a go. Okay, true or false, hydrogen ions reduce aluminium. Well, let's have a look. Is aluminium being reduced up here? Certainly not. It's being oxidized. So that's going to be false. Electrons flow from the aluminium electrode to the inert electrode. Well, the aluminium is most certainly giving up electrons, freeing them up, and so they are going to flow to the inert electrode. It's true. The mass of the cathode will increase. Let's have a look. Will the mass of the cathode increase? The cathode is where this hydrogen reaction is taking place. And so it looks like we have an inert cathode. And so that is false. We have another one of these fantastic tables. So let's go through it. Predict the reaction in a silver magnesium voltaic cell. What should we do first? Well, let's put the half equations in. We know the magnesium is going to give the ion, it being more reactive than silver. And the silver ions are going to form the solid. So we know that the magnesium must therefore be the anode and the silver will be the cathode. And we know the anodes are negative and cathodes are positive. And so we've worked this out because our reactivity series tells us the magnesium is more reactive than silver. So which is going to change in mass? Evidently, the magnesium is going into solution, so it's going to decrease in mass, and the silver, more solids forming, so it's going to increase in mass. The salt bridge, we're going to get nitrate ions moving into the magnesium half cell to balance the charge, and we'll get those potassium ions moving into the silver half to balance the charge. The electron flow, as always, is from the anode to the cathode, from magnesium to silver. Okay, let's annotate this diagram for silver magnesium voltaic cell. We'll write down the overall equation first. We've got the magnesium being oxidized and the silver being reduced. Write this cell notation down the bottom there. We've got the magnesium anode with magnesium in solution. You've got silver, silver ions in solution, and you've got the solid cathode. Okay, can you take your time and clearly label that diagram? Let's have a look at a few questions. See example 4. In an operating zinc-lead electrochemical cell, lead 2 ions A, lose electrons at the anode, B, act as a reducing agent, C, gain electrons at the cathode, D, oxidized. If you get a question like this, what you should do is scribble down the equation for the reaction first and then for the half reaction. So let's do that. We've got zinc is more reactive, so the zinc will form the ion and the lead ions will form the solid. So oxidation is the zinc forming the ion, and reduction is the lead ions forming the lead. So which one is going to be correct? Lead 2 ions are acting as, well, if the lead is being reduced, it must be acting as the oxidizing agent, and therefore it gains electrons at the cathode. Example 5. Which statement is correct for a spontaneously operating silver hydrogen electrochemical cell? A. Silver ions are oxidized at the cathode. B. Silver metal is oxidized at the anode. Hydrogen ions are reduced at the cathode. Hydrogen gas is oxidized at the anode. Again, let's write the reaction down. And I'm going to write down those half reactions. Okay, have a think which is correct. Let's pause. And that's right. Remember that reduction happens at the cathode and oxidation at the anode. We see the hydrogen gas is oxidized at the anode. Example 6. Which statement is true concerning a magnesium nickel voltaic cell? Magnesium oxidizes nickel 2 ions. Magnesium reduces nickel 2 ions. Magnesium reduces nickel. Magnesium oxidizes nickel. So let's write the reaction first. And for the half reactions, have a think about it. That's correct. Magnesium reduces the nickel 2 ions. You can see here, magnesium is being oxidized, so it must be the reducing agent, and it's giving 2 electrons up, and those 2 electrons are being used to reduce the nickel ion to nickel. Okay, voltaic cells. Let's look at some batteries. Example 1, we've got a dry cell of an alkaline battery. If you look at this picture over here, you can see that the zinc anode is kind of light grey here. The manganese oxide cathode is the darker brown here, separated by this ion conductor separator. You've got a positive connection here, which will run through whatever you plug it into. You've got the negative terminal here. So the circuit would go between the positive and negative, and you've got electrons moving between these two here. What's going on at the anode? Let's have a quick look. Well, you've got zinc reacting with hydroxide ions to give zinc oxide, water, and giving up electrons. And obviously, you've got these hydroxide ions, that's why it's called alkaline battery. At the cathode, we've got magnesium oxide reacting with the water and the electrons given out by the negative terminal to give us this magnesium oxide here, and hydroxide ions are given up. Next, we've got fuel cells. The fuel cells use hydrogen. Let's have a quick look over here. You've got the anode, which is where the hydrogen's going into, and this is giving the electrons. It goes through the current, and then the electrons bond with the positive hydrogen ions and oxygen to give water. So water is given out. So it's a very environmentally right on battery. So let's have a look at the anode. Well, we can use hydrogen gas to give us those protons and the electrons, or we can use methanol in water, and both are used. You can make cells with either. The cathode, you've got the oxygen gas reacting with those hydrogen ions and the electrons to give water. And you should find out what the advantages and disadvantages of these fuel cells are, and just scribble them down in your notes. Lastly, we've got lithium ion batteries. The anode, we've got some graphite, which is doped with lithium. And over here, the lithium goes into kind of a matrix, it gets trapped into a matrix. And obviously we use these lithium ion batteries in mobile phones and laptops. The anode, you've got this lithium graphite, which gives graphite and a lithium ion and kicks out an electron. And you've got cobalt oxide reacting with lithium at the cathode and using that electron to give lithium cobalt oxide. The electrolyte in these batteries are lithium salts such as lithium hexafluorophosphide in an organic solvent. And you should also find out some advantages and disadvantages of lithium ion batteries. properties and scribble those down on your notes. Okay, that's it for that presentation. Splendid. Goodbye.